Today we will discuss about the intensity distribution in case of Fraunhofer single slit. Let us consider again there is a slit AB and the parallel rays are obtained with the help of convex lens L1. The width of the slit is A and these are converged with the help of another lens L2 on the screen. And let us again consider the midpoint of the slit is C and opposite to slit there is a midpoint on the screen O. At any point P, these rays are converging with the help of the lens L2. We know that there is a path difference in between BP and AP, and this path difference is given in the terms of the angle of diffraction made by the waves given as A sin theta. This A sin theta gives us two conditions, one condition for minima and the second condition for maxima. When A sin theta is equal to n lambda satisfied this condition, we obtained a dark fringe at the point P. When A sin theta is equal to 2n plus 1 lambda by 2, then this equation gives the condition for the bright fringe at the point P. Now we will discuss about the intensity of all the maximas and minimas. To obtain the conditions for the maximas and minimas, let us consider the slit A and B are divided into large number of points and we are taking n number of points. The waves coming from these points have a phase difference of delta in between them. A and B shows a path difference of A sin theta from A to B. Hence, they are also showing a phase difference of 2 alpha corresponding to this path difference A sin theta given as 2 alpha is equal to 2 pi upon lambda into A sin theta, where we are taking alpha is equal to pi upon lambda times of A sin theta. Now we have divided this phase difference 0 to 2 alpha into n parts. So 2 alpha upon n is equal to the small deviation between these two waves, and it can be given as 2 pi times of A sin theta into n lambda according to our condition. We know that all these waves coming from different points of the slit are approaching to the point P on the screen. At point P, we are obtaining the resultant of all these waves. Hence, at point P, we are getting the resultant of all these n waves which are moving from the slit AB towards the point P, where y1 represents the wave which is coming from the point A to the point P, and it is given as r sin omega t. This r is representing the amplitude of the wave coming from the point P. All the waves are coming from the same source, hence all waves have same amplitude. Second wave that is coming from the next point is given as r sine omega t plus delta, where delta is representing the phase difference in between the two corresponding waves. Third wave is given as r sine omega t plus 2 delta. It means this is the wave coming from A. This is our first point wave. This is the second wave, third wave, which is coming from the second point. If there is a phase difference of delta in between these two waves, then there is a phase difference of 2 delta in these two waves. Hence, similarly, we will obtain for the equation for the last wave coming from the point B, that is given by r sine omega t plus n minus 1 delta. As we are seeing that when there is a subscription of 1, then we have plus 0 times of delta. When there is a subscription of 2, then we have 1 delta. When there is here 3, there is 2. For n, we will get n minus 1 times of delta. Hence, using all these wave equation, we find out that the resultant wave is given as the addition of all the waves given by r sine omega t plus sine omega t plus delta plus sine omega 2 plus 2 delta and so on. The last term will be sine omega t plus n minus 1 delta. These sequence of sign can be written as y is equal to r sine n times of delta by 2 divided by sine delta by 2, and this series can be written as sine omega t plus n minus 1 delta by 2. This term is representing the amplitude of the wave. Hence, we write as amplitude of the wave is given as A is equal to r sine n delta by 2 divided by sine delta by 2. Using the relation in between delta and alpha, from here delta is equal to 2 alpha by n, we can convert this whole equation in the form of alpha. Hence, we can write this A is equal to r sine alpha divided by sine alpha by n, where alpha is very small and we know that alpha is divided into n parts, and alpha by n should be very small. Hence, instead of sine alpha, we can write this equation as alpha by n. Therefore, the amplitude of the resultant wave can be written as A is equal to r sine alpha divided by alpha times of n. R is representing the amplitude of single wave, and as we know that number of waves is n, then nr is the maximum amplitude which can be obtained by the superimposition principle of the waves. It is the maximum amplitude of the wave, hence it can be written as A naught. Therefore, A is equal to A naught sine alpha by alpha. As we are discussing about the intensity of the fringes which are obtained with the help of Fraunhofer diffraction on the screen, and intensity is directly proportional to the square of the amplitude. Therefore, from above relation, we will find out that I is equal to A naught square sine square alpha divided by alpha square. This is the condition from where we get the bright fringes intensity as well as the dark fringes intensity. First, we will discuss about the intensity of central maxima. In case of central maxima, the ray is coming from A and from B. They are covering equal distances. Hence, the path difference in between them is equal to 0. Hence, we know that alpha comes out to be 0 in this case. Therefore, sine alpha is also equal to 0. Then sine alpha upon alpha, that is 0 by 0, is an undefined condition. To obtain the solution for the intensity, we will use the L'Hospital rule, and according to which, if limit alpha tends to 0 and we have to solve for sine alpha upon alpha, we have to take the differentiation of the above term as well as the differentiation of the below term, and for alpha is equal to 0, we will get the total result is equal to 1. Hence, the intensity is equal to A naught square, and A naught square is the maximum intensity. Hence, the central maxima is the brightest maxima. This is with bright maximum intensity. Next condition for the first secondary maxima, that is the maxima above and below obtained from the central maxima, is given as, now again, I is equal to A naught square. This formula will find out the intensity. Again, we have to find out the condition for maxima, and value of maxima is independent of A naught square, because n into r square, it is a constant term. It means the intensity is depending upon the angle alpha, and sine alpha is maximum only when alpha is equal to pi by 2, 3 pi by 2, 5 pi by 2 or 7 pi by 2 and so on. It means in the generalized form it is given by 2n plus 1 pi by 2. For the first maxima, secondary maxima, we have to put n is equal to 1. It means alpha is equal to 3 pi by 2. Then what about the intensity? Intensity comes out to be sine square 3 pi by 2 divided by 3 pi by 2 whole square, as 3 pi by 2 is equal to 270 degree. Then sine square 270 degree, that comes out to be 1. Hence, the intensity is equal to 3 pi by 2 whole square, and this is equal to 1 upon 22 times of the maximum intensity of the maxima. Therefore, the first secondary maxima have an intensity of 1 by 22 times of the central maxima. Similarly, the second secondary maxima have the intensity when n is taken to be 2. When n is equal to 2, alpha comes out to be 5 pi by 2, and we will have I is equal to A naught square, and again sine square 5 pi by 2 comes out to be 1, and in the denominator we will find out 5 pi by 2 whole square. The result comes out to be 1 upon 61 times of A naught square. It means when we will draw a intensity graph for the central maxima, for the first secondary maxima and the second secondary maxima, the intensity of the central maxima, if it is denoted by I naught, then the intensity of the first secondary maxima is 1 upon 22th times of the intensity of the central maxima. If we draw the intensity for the second secondary maxima, it comes out to be 1 upon 61 times of the maximum central maxima. Similarly, we will obtain the same pattern above the central maxima. Now, we will discuss about the condition for minima. Condition for minima is given by a sin theta is equal to 2n plus 1 lambda by 2. How we will obtain the intensity in the above case? We know that the formula for the intensity comes out for the single slit Fraunhofer diffraction is a naught square sine square alpha divided by alpha square. Intensity will be minimum or when only when the alpha is equal to 0, pi, 2 pi, 3 pi and so on. It means when alpha is equal to n pi in general form, only when then the intensity comes out to be 0. It means when alpha is equal to n pi, and according to our relation, alpha is given also as pi a sin theta upon lambda, then according to this relation, we find out the condition for minima. A sin theta, we will cancel out pi from pi, we will have n times of lambda. It means sin theta is equal to n lambda upon a. We know that in optics angles are taken very small. If sin theta is very small, sin theta can be changed to theta, and it is given by n times of lambda upon a, where n is the number of fringes, lambda is the monochromatic wavelength taken, and a is the width of the slit. For minima, we have the positions lambda by a for the first minima. For second minima, n is equal to 2, we have the diffraction angle 2 lambda upon a. Similarly, we will get the different positions for the minima. Now, if we draw a graph in between the angle and the intensities of different type of fringes obtained with the help of single slit, for theta is equal to 0, it means we are discussing about the central maxima, and for central maxima we find out the intensity is maximum, that is taken as I naught, and I naught is equal to A naught square, where A naught is given by n r, and this intensity is equal to n r square. What are the positions where we will get the condition for minima? We know that for lambda upon a, we will get the condition for minima. It means if this is lambda upon a, we will get first minima. Here also the distance is lambda upon a, we get the first minima. For second minima, we have the condition 2 lambda upon a. When the angle theta is equal to 2 lambda upon a, we get the next minima. Similarly, at this side also, at position 2 lambda upon a, we get the minima. Next is 3 lambda upon a. On the other side also, there is 3 lambda upon a. Then what are the positions where we will get the condition for maxima? We know that a sin theta is equal to 2n plus 1 lambda by 2 gives the condition for maxima. And to obtain the angle relation with the wavelength, again we are taking the consideration that theta is very small. It means theta is equal to 2n plus 1 lambda by 2a gives the condition for maxima. Substituting the value n is equal to 1, we get the first maxima about the central maxima, that is 3 lambda upon 2. 2a. Similarly, for n is equal to 2, we get the next maximum position 5 lambda upon 2a, and so on. It means at this position 3 lambda upon 2a we will get our maxima, and at 5 lambda upon 2a we get our another maxima. Similarly, on the other side, at 3 lambda upon 2a we get our maxima, and at 5 lambda upon 2a we get our another maxima. These are the points of maxima and minimas alternately. Now, what happens to the intensity? As we discussed, the central maxima has the largest intensity. This is the position of minima, this is the position of minima. Then we have to draw like this the central maxima. Next maxima is corresponding to this point, and we know that the next maxima has a intensity of 1 by 22 times of the central maxima. Then we have to draw a small half wave. Similarly, on the next side position we are taking the same, and at 2 lambda upon a we are taking the minima. Similarly, at 2 lambda upon a we are taking the minima. At 5 lambda upon 2a we are taking the next maxima, but with a intensity of 1 by 61 times of the central maxima. Similarly, we will draw the on the another side, and this is the fringes pattern or the intensity distribution for single slit Fraunhofer diffraction.